I'd like to thank the organizers for organizing this really nice workshop and for inviting me to come. Thank you so much. In this talk, I'm going to tell you about a new non-equilibrium phase of matter, a so-called time crystal that we've realized in our lab, and that's very well aligned with the theme of this workshop. And so this time crystal requires a many-body system with strong interactions, and for this purpose, we use a platform that's so far been mostly applied for the purpose of quantum computation and quantum sensing. And so this. Okay, this platform are atom-like defect centers in diamond. And you can see here an image of such defect centers, and they nicely turn a diamond from transparent into beautiful colors. For instance, if you have nitrogen defects in diamond, then you get a yellow to orangish, or orangish to reddish color. And so these color centers are, have the potential to provide us with the best of both worlds, and that is on the one hand side, the excellence coherence of isolated atomic systems and also the strong interactions in these atomic systems. And on the other hand, scalability and interoperability of solid-state systems. So for the purpose of our research, we chose to work with NV centers, nitrogen vacancy centers. And they're just one of many stable impurities. And you can see an image here of a diamond lattice. And so the nitrogen atom is replacing a carbon atom in the diamond lattice, and there's a nearby vacancy. And so the two form a very stable defect that can be regarded, in principle, as a nature's own trapped ion. And it has nice optical properties, which is it has a very stable, narrow emission line at 637 nanometers if you cool down the diamond. And you can individually isolate NV centers using a conformal microscope. I'll show you an image here of a 2D scan the surface of a diamond, and all of these individual bright spots that you can see here are NV centers. Why it's mainly used is because of its excellent spin properties. It's a very nice spin qubit because its ground state consists of a spin triplet. It has a zero field splitting, and you can actually rotate the spin between these two different ground states using microwave fields. And people have achieved relatively long coherence time on the order of milliseconds. You can polarize the spins optically, and you can also read it out optically, and that you can even do at room temperatures. And you can couple these electronic spins of the NV center to a nearby nuclear spin, and in this way you can generate a very long-lived memory on the order of seconds. Now, for our purpose of realizing a strongly interacting many-body system, we need to generate a sample that has a very high density of these NV centers. And this has been done by our sample providers in Japan. And what they do is they use an HPHT-grown diamond with an initial density of NV centers of nitrogen atoms of 100 ppm. And then they irradiate it with high-energy electrons and perform annealing at the same time. That means heating the sample up, such that these NV centers can form immediately. And by actually performing this step for half a year, they finally were able to provide us with this really nice black diamond. It's black because of this extremely high density of NV centers. And so this is now an interacting many-body system, and what are we using it for? Well, generally, people are interested in studying quantum many-body dynamics in different areas. It plays an important role in the simulation of complex quantum systems. It allows for enhanced sensing in quantum metrology. It gives rise to new regimes of quantum statistical mechanics, and finally can also lead to novel dynamical phases of matter. And in my talk, I will touch upon the bottom two aspects.
On average, how far are the emicenters?
5 nanometer.
Okay, so the interactions between them are still quite strong. Yes. Yeah.
I'll have a slide with more details. Okay, so here I'll present you with a quick outline of the talk. I will first review what a time crystal is, or what we call a so-called discrete time crystalline order, and then jump into our experimental platform, so-called black diamond platform, and show you experimental evidence for this new non-equilibrium phase. And then the second part of my talk, I want to focus on, one particular aspect of this time crystal, namely that it's a very nice tool to study the underlying quantum thermalization occurring in the system. Okay, so what's a time crystal? Well, it refers to a phenomenon where the time translational symmetry is continuously broken. And so it was Frank Wilczek who proposed this idea in a very simple setting in 2012. He imagined charged particles that are sitting on a ring, and there is a magnetic flux threaded through it along the vertical direction. This leads to a constant current flow along the ring, constant time-independent current flow. Now, if you turn off this magnetic flux and instead turn on strong interactions, these interactions can be attractive or repulsive, and the system will try to minimize their interaction energy. And so with attractive interactions, it will try to bunch up all of the particles to one location, and with repulsive interactions, have them be as far away from each other. And so there will be some spatial symmetry breaking involved. And now if you combine these two, what you'll end up as with a situation where you have these bunch particles or spatially arranged particles that are now oscillating on this ring and producing thereby a time periodic current. It's no longer constant in time, but it's periodic in time. In other words, you start out with a Hamiltonian that is time independent, but nonetheless, you find an observable in your system that is time dependent, that shows such a periodicity. And if that is true, then you call this a time crystal. The idea, you can see this very much in analogy to a space crystal, where you can start out with your system in a liquid or a gas phase where particles can occupy each location in space. But then at the phase transition to a solid, they'll arrange in this periodic pattern in space. And they'll be, arranged at multiples of the lattice constant, for instance. And as for this space crystal, where you would expect that, upon pushing on this crystal from the side, it shows a certain rigidity to this perturbation and keeps its crystalline structure. If you do the same thing to this time crystal, it should also keep this time periodic structure. All right, well, this initial idea did sound plausible for a certain amount of time, but people were also arguing a lot. And relatively soon after, they figured out for a system in equilibrium, such time crystal cannot exist. If you have a system that you can describe with a local Hamiltonian, system that's either in its ground state or a thermal ensemble, it cannot show this phenomenon of a time crystal. In other words, if you have a system in thermal equilibrium, then the observables by construction are time independent. So there's nothing to be broken in first place. But fortunately, that's not the end of the story, because these arguments, they do not apply for systems that are out of equilibrium. Systems that you periodically drive, and that are non-thermalizing interacting systems. So systems that are localized or only very slowly thermalizing. And what theorists have shown in 2016 and 17 is that these systems can show a phenomenon called discrete time crystals. What are these discrete time crystals? Well, it's kind of the same idea as the original proposal from Wilczek, but now you're applying this periodic drive, so you're already breaking down the continuous time translational symmetry into a discrete one. Right? But now the system can still spontaneously break that discrete symmetry further down. And so then that's what you call a discrete time crystal. And so you require, again, a strongly interacting system. And now you have the system be subject to a time periodic Hamiltonian with a Floquet unitary that has these unitary operators H1 and H2, for instance, and a Floquet period tau. And now you time evolve your system under this Floquet operator. You look for an observable in your system that shows a periodicity that is a multiple of this Floquet operator, or in other words, that is at a subharmonic of your drive frequency. Because if you can find such a subharmonic response, then it's really interesting because the system itself has chosen this subharmonic response. And if you can show that this subharmonic response is not just due to fine-tuning of certain parameters, but that it's robust against perturbations, and that it's long-lived, then you call this a time crystal. Okay. This is all about the definition of the time crystal part. If you have any questions, please raise them now. Now I'm going to switch to the experiment. Yes?
So I have two questions. I guess one is, I didn't quite understand what you mean by rigidity in time. And the second one is, what is it obvious that you need quantum mechanics in this picture, or like to get a time crystal, or is it both classical and quantum, or it's just quantum?
Yeah. So for the first thing, what means rigidity? So for a space crystal, rigidity means that it keeps its sort of it keeps its solid features, right? For instance, that you have this periodic arrangement of that you have a certain lattice constant, right? Now, if you have, in this case, for the time crystal, also the rigidity means it has to keep this subharmonic response. This frequency is not going to change upon perturbation. If it has chosen, to show a subharmonic response at twice of the, at half of the drive frequency, then it's going to be fixed at that frequency. Right. It's not going to change upon you perturbing the system.
Right.
So this is rigidity.
What do you mean by perturbing? Like changing the original driving system, frequency, or like because in a real crystal I can imagine
you can press, you can push on it.
But what is the perturbation you're thinking?
Well, and you'll see it later, and so we're actually starting to rotate these spins,
okay.
And they can actually compensate for imperfect rotations. This is the perturbation in this case. I'll show it when I'll go into detail of the Floquet unitary that we use for our particular case. Yes. And whether it can exist in classical or quantum systems. So what's so special about the quantum system is that such a time crystal can exist in a closed system. You're driving the system, but the system is not going to absorb energy. It's not going to heat up. The system will, stay cold and, in best case scenario, keep this time crystalline structure forever. If you do that with a classical system and you drive this strongly, it'll start absorbing energy and it's going to heat up to infinity. And the only way you can then get this phenomenon of a time crystal is when you introduce dissipation. Then you can get similar aspects. Yes. For closed system, it only works in the quantum case.
You need some extra.
You need some extra phenomena like many-body localization, which doesn't allow the system to heat up, or a very slow thermalization, such that you can see this for an extended period of time.
So in a way, it's the many-body localization that brings the quantum mechanical.
Yes. Yeah. Or you can have, there's also this another special case of so-called pre-thermal time crystals. These also exist. You don't necessarily need to have the phenomenon of localization. There you simply make sure that the drive energy scale is so high that it also cannot get absorbed by the system immediately. It'll get absorbed eventually, so the system will sort of saturate to some pre-thermal state, and they'll show this sort of a time crystalline behavior for some finite amount of time before it heats up to infinity. Then you can have this phenomenon as well. Yeah.
Thanks.
You can barely see it, but you should be seeing our experimental platform, which is a coplanar waveguide structure, so some golden chip, where we deliver the microwaves to this black diamond sample that sits here in the center. And from below, we have a confocal microscope objective to also bring light fields to the sample. Here you can see again an illustration of the NV center. So this ground state splitting that I was talking about, that is what's so special about the NV center, is at 3 gigahertz, so that's about the frequency range of the microwaves that we apply, around 3 gigahertz. And so we can, as I said, prepare and read out the spins optically, and then we can manipulate it with microwaves. And so, as we actually illuminate the diamond, the black diamond, with this green light that we use for readout and initialization, this diamond really fluoresces so strongly red that you can see it with the bare eye. Okay, so some more details on this black diamond. As I said, we have a density of around 45 ppm of NV centers. That corresponds to a mean distance of only 5 nanometers between nearby NV centers, results in 400 kilohertz of dipole-dipole interaction strength. We work with a relatively large ensemble, so within this probe volume that we address with the confocal light beam, we excite and measure around 1 million of these NV centers. And we can control the density of these NV centers using magnetic fields. The idea is that NV centers can grow along be created along 4 different crystallographic axes within the diamond. And so by changing the orientation of the magnetic field, you can Zeeman shift or bring different groups into resonance or out of resonance. So when you, for instance, take the ESR line, scan over the ESR lines of these 4 different groups, then in this particular magnetic field configuration that we chose here, the group A and group D are split off, and group B and C are degenerate in frequency. Okay. And so when we zoom into now one of these ESR lines, what we find is that the ESR line is much broader than what you would expect from a single NV center. And the reason is that there's these leftover nitrogen atoms that have not been converted into NV centers, and they produce a random on-site potential offset at the location of the NV centers with a strength of 4 megahertz. That means we're working with a strongly disordered but also strongly interacting sample. And this sample can be described very generally with a Hamiltonian if we go into a spin 1/2 submanifold, which we can do by applying a magnetic field and Zeeman shifting the levels. And then you can describe the system as applying a Rabi drive along the x direction with some strength, or the y direction with a certain strength. You have this on-site potential, it's acting along the z direction with this 4 megahertz of strength. And you have the dipole interactions that scale as 1/r³, and that contain both a spin exchange part as well as an icing term. So the first thing we did when we received this new sample is we studied depolarization dynamics. What we would do is we would prepare 2 of these spin groups that I was talking about in oppositely polarized spin states and bring them into resonance, have them interact with one another, and look at the duration it takes for these orthogonally polarized spins to depolarize. And so when you plot polarization as a function of time of one of these 2 groups, what you find is this is on a double logarithmic plot. You see the decay is extremely slow, and this is actually on the order of 100 times the interaction time. So it's extremely slow, sub-exponential thermalization dynamics.
What temperature is it? What is T1 and T2?
what temperature is this? So effectively, if you prepare it in a polarized state, you're sort of at an infinite temperature.
Yeah,
because
but
you have
the temperature of the diamond.
Oh, it's at room temperature.
It's at room temperature. So what are the T1 and T2? What's this temperature?
So the T1 timescale is on the order of 100 microseconds, and the T2 is on the order of 1 microsecond, 800 nanoseconds. So why is there such slow thermalization? Well, the reason is that for thermalization to occur, spins need to find a resonant partner to spin flip with, and such resonances are suppressed because of the disorder. And so if for our particular case where we are in a three-dimensional system with one of our R-cubed interactions, what you would expect from Anderson picture is that you're in the critical dimension. It's neither ergodic nor localized, but it's in a critical dimension where you expect power law decay of polarization. With a power law exponent that now depends on the strength of the disorder. And that's exactly what we see. So when we perform resonance counting of having a central spin that's pointing up and trying to find a resonant partner around with which you can spin flip, then you'll find that this the polarization decays according to a power law, and so we can actually fit our data with power laws. And if we vary the disorder strength in the sample, which we can actually do, we find that this power law exponent changes in accordance with Anderson. Yeah.
Could you imagine doing this experiment on this surface?
Just on the surface in 2D?
Yeah.
Yeah. Well, this bulk sample, it's not so easy to isolate. Just you would need to. Yeah, you have to create a very large magnetic field gradient in order to shift them spectrally away, so that we can just address those. We're looking into that. Also, you can just fabricate a sample that's two-dimensional. You can do this at lower density, achieving a two-dimensional high-density sample. That's not so easy, but that's the next thing we asked our collaborators to provide us with. So we'll see. Yeah.
So you would actually, or I would actually expect that the system delocalizes, right? Because you also have interactions present in the system. So since the Anderson case is already critical or marginal,
it's exactly. So this is unclear till today. So there's these two. Anderson is a single particle picture, non-interacting. Now we have an interacting system, and there's this paper by Buren that says that if you have interactions, then there can be many-body resonances, and they facilitate delocalization. And so then he puts a more stringent condition on the transition to a many-body localized state. And actually then in 3 dimensions, we should also still see rather a little more ergodic behavior than what we're actually seeing. So nobody has shown that experiment in the year. That's why it would be very interesting to go to 2 dimensions, because then according to Anderson, we should be localized, while according to Buren, we should see this critical behavior.
So what is the typical time scale of the Hamiltonian in that scale now? Microseconds?
Of the Hamiltonian,
some coupling exchange coupling.
So the coupling is this 100 kilohertz, or 400 kilohertz, so called.
Kilohertz, okay.
Yeah.
So is this a zero magnetic field where all the different orientations are degenerate, or is it finite magnetic field?
This is in a magnetic field configuration where they're all split, but the 2 groups that we work with, they're only split like a little bit, while the other ones are really split far off. And these 2, to bring them sort of to have them orthogonally polarized and bring them into resonance, we do that in a kind of a driven case in a rotating frame.
So you only get optical contrast for when they're aligned, right?
Here the polarization is just the polarization of one of the 2 groups, but in principle we can read out both separately.
Okay, so you don't know that it's going into the second group, right? Just you know that one
we did read it out, and we did see that it was going
into the second group.
So it goes into the second group, but then eventually there's actually processes in our system where the polarization is completely lost. So
Just
initially it's
energy
exchanged,
match-
and
energy
then
match
actually-
closes
yes.
into these two groups.
yeah. But eventually the T1 dynamics, the depolarization mechanism is that these NV centers, they couple to, we call them fluctuators, that's sort of NV centers that have a very short lifetime, because they're close to a sort of neutral, so NV0 that steals their charge. And so then in this process of charge hopping, the spin state is not conserved. And so this way they lose their polarization
This is
eventually.
like instead of permanent dipoles, like induced dipoles, so then they dissipate, or how does it work?
This charge state dynamics, we don't know. We've only been able to, you can detect these NV0 states separately from NV minus. So we've been able to actually show that there's some dynamics of, enhanced NV0 population and then sort of a diffusion back to an equilibrium. So you can prepare you can actively, so when you polarize the system initially, what will actually happen is that you'll also induce these charge hoppings. And then it takes some time for the system to equilibrate and to have some equilibrium distribution of NV0 and NV minus. And so you can show that, you can see this charge hopping. Okay, yeah, so we call this a critically slow thermalization, and that paper will soon appear on PRL. Okay, so in this very slowly thermalizing system, we are now trying to implement a time crystal. And the idea is the following. We came up with a Floki cycle that looks like this. It has an interaction part, and it has a rotation part. For this particular case, we just work again in a spin 1/2 submanifold. We initially prepare all the spins along the x direction, then point along the x direction, and then we have them interact here for this duration tau1 with an interaction that's only of Ising type. So we turn off spin exchange interactions, only Ising interactions, and then we perform a global spin rotation of all of the spins by a rotation angle of about pi. And we repeat this n times, and we measure the remaining polarization along the x direction. And now we can introduce a perturbation by simply performing an imperfect rotation. So not rotating by pi, but rotating by pi plus epsilon. And this epsilon corresponds to the perturbation. And so something else I want to tell you here is that we cannot change the interaction strength. So in all of these data I'll show you, what we'll do is we change the interaction time. What I will also show you is that what in the end matters is the product of interaction strength times interaction time. So, and we only have an easy handle on the interaction time. Okay, how do we turn off the spin exchange interactions? For that, what we're actually doing is that we use the technique of spin locking. So here you can see the Hamiltonian of the system in a dress state basis, where we've already prepared the system along the x direction. And so if you now apply a strong drive along the, if you drive the system now strongly with a Rabi field along this x direction, what will happen is that you effectively, the spin exchange part here will effectively average out. And so what you'll be left with is only the Ising interaction bond. And so then during the interaction time, what we'll have is this Rabi drive along the x direction and this Ising interaction. And for the rotation part, it's simply a quick global rotation around the y-axis. Let's start with the simplest case. We have a very short interaction time and a perfect rotation of pi. What we find is that the polarization in the system decays, it oscillates up and down as a function of Floki cycles. And when you take the Fourier transform of the signal, you find a subharmonic at half of the drive frequency. Now you'd imagine, is this this is a perfect time crystal, right? Because it shows the subharmonic response, but it's very trivial, right? Because you perform a perfect pi rotation. If you do this twice, your spins will align back to the original direction. So you can actually also prove that it's not a time crystal in this trivial case where you don't have interactions present, because if you now introduce perturbations, do this by 3%, rotate 3% away from pi, you immediately see a beating structure emerging in the time signal. So when you take the Fourier transform, you see two sidebands emerging. So the subharmonic peak was not stable. It did split into two side lobes. And so this can certainly not be called a time crystal. It's not rigid. But interestingly, when we increase the interaction time, increase this by a factor of 10, and keep the perturbations on, the system recovers and shows this nice subharmonic peak again. A very sharp peak at half of the drive frequency. And this is what we associate with this 2T periodic order and with a discrete time crystalline order. Because we can see here that it's the interactions that stabilize this time crystalline order.
The peak height increases with the time of the interaction. So
Yes, peak height.
above is like 120 and below is like 40, it has increased.
I think for this particular case, what we did is as you can see here, there's this initial transient here that occurs, and then you see that actually the lifetime here is even longer than in this case, right?
Yeah.
And what we usually neglect this initial transient, and we want to look at the long time behavior of this time crystal, and that contrast is actually larger.
In the third case, if you keep increasing the perturbation, does it go?
Eventually, it will split.
What's the
There's a phase
dependence on
boundary.
that? Is there any? Is there some critical value at which it just goes away?
Correct. Yes. And I'll show you. There's a simple intuitive picture, and you can, it's a closed system, and you can solve it self-consistently in a mean field approach, and you'll find that yes, this maximum perturbation strength does depend on the product of interaction strength times interaction time. Okay, so we would investigate the robustness of the system against these perturbations, and so here we have plot perturbation along this axis, and plot here the Fourier spectra for different perturbation strength. And in the case of weak interactions, we see that this peak at half of the drive frequency is quickly disappearing and side lobes emerge, and if you go into the strong interaction regime, then you see it being robust over a wide range of perturbations. And so the intuitive picture for this is that of a single particle on a Bloch sphere. Imagine that you perform an imperfect rotation here in the non-interacting case, then it simply results in a phase lag of the system. So there will be no closed path. Because of this phase lag, you'll eventually have these side lobes. And so in the case with interactions now, the interactions can compensate for this phase lag, and the system can actually find a closed trajectory on the Bloch sphere, which is then 2T periodic. And now you might ask yourself how these interactions can perfectly compensate for the perturbations. And actually, this is not the right question to ask. You should actually rather ask whether there are closed trajectories for this perturbation that you apply. And if there are closed trajectories, then you can actually show that these such 2T periodic order can exist for any initial state. Okay. To better characterize this DTC order, what we do is we define a so-called DTC fraction, which is the spectral weight of the subharmonic peak in the Fourier spectrum. And so we choose to take the Fourier transform only of the after driving the system for a lot of these floppy cycles where such initial transient have decayed away. And then we can plot this crystalline fraction as a function of rotation angle, and you see that for large enough interaction times, you see this plateau emerging, and then it eventually goes to 0. And now you can come up with a phenomenological phase boundary defined as sort of the point where the crystalline fraction has decreased to 10%.
Short question, so this initial transient that you are mentioning, is it again due to these fluctuators, as you said before, that there are some fast decays that you don't want to actually study in this setting, so that's why you look at this longer time window? Or what's causing this initial transient?
So this initial transient certainly is, so it's not this charge dynamics, because that happens on, we actually particularly take some wait time after we prepare the system to make sure that this charge dynamics has decayed away in some equilibrium situation. And then we start with this floppy drive. So that's not the reason. What we think is the reason is that, you know, you start with some initial state, and what will happen is that these eigenstates of this time crystal are not necessarily exactly equal to your initial state, and so your system will get projected into the eigenstates of this time crystal. And for this projection, right, if it's not perfectly, so for each individual spin, this eigenstate might be oriented along a different direction, slightly different direction, and so it will get projected into this eigenstate and thereby actually lose some of its polarization. And once it's in this eigenstate, it's then protected. Okay, so this is one way to characterize the system. Another way to characterize it is look at the decay rate of this time crystalline signature, of this oscillating signal. And so what we do is we define a window of width m, and we sweep this window through our time signal, and we look at the peak height locally. We take the Fourier transform in this local window, and we extract the peak height. And we can plot this peak height now as a function of the location of this sweeping window. And what we find is, you know, after this initial transient, you have so you get a by exponential decay, and this initial decay is this transient behavior, and then the long time dynamics is what we are really interested in. And so we can fit an exponent to this long time, and we can plot this as a function of the perturbation strength. What we find is that within the phase boundary that we've extracted with this other method, we find that the decay rate is independent of the perturbation strength. So the system is really robust against perturbation as long as it's in this time crystalline phase. Once it exits it, the decay rate also increases drastically. So we can then plot the full phase diagram. Here I plot it as a function of rotation angle and interaction time, with the dots here indicating the DTC fraction. Blue color is a high DTC fraction, and then it reduces towards the phase boundary, and these yellow diamonds denote this phenomenological phase boundary. Okay, so what you see is that initially the phase boundary increases linearly as you increase interaction time. And this can be seen very well, you know, or you can predict this theoretically using this closed path argument that I initially introduced. So you can solve the eigenvalue equation that you have for a closed path for a stable solution, and you'll find a stable solution as long as this perturbation angle is smaller than the characteristic product of interaction time times interaction strength. And so with this mean field prediction, this mean field prediction agrees very nicely with our experimentally extracted phase boundary. Now what we also see from this phase boundary is that at longer times the phase boundary saturates and even starts bending inwards. And so there's something else that comes into play. Well, what is it? Well, so far we've neglected that the spins can thermalize. And this is actually where thermalization starts setting in. So far we've, thought of a closed system with an effective Hamiltonian description. But now if we assume that the system can start absorbing energy from the drive, then it becomes open. And so initially, actually, if you think of thermalization dynamics, then what can those be? These can be single spin flips, but these are suppressed because of this large icing field that's present. Now you can have double spin flips, and these are suppressed because of the disorder present in the system. But now, when you increase the interaction time, that means that the Floquet drive frequency gets smaller. Right? And so as it gets smaller, it becomes comparable eventually to the disorder strength in the system, because that's the largest energy scale we have in the system. And so it starts renormalizing the disorder. And so then it's this peculiar interplay of disorder drive into interactions that now gives rise to a slow thermalization dynamics. And so you can again do resonance counting for a central spin that tries to find a resonant partner nearby, and taking into account this renormalized disorder strength, what you'll find is that you'll expect that the system shows a decay rate that's exponentially suppressed. Exponentially slow, but with this, if you look closely in this exponent, you'll see that this predicts a phase boundary that moves inwards with the square root of the interaction time. 1 over the square root of the interaction time. And this is exactly what we see experimentally. So in this regime, we describe it as a critically slow thermalizing DTC. So we see that this DTC is a very sensitive probe of the underlying thermalization dynamics. And so we can make use of this, of its sensitivity by now looking at different types of interaction Hamiltonians and what effect that has on the underlying thermalization dynamics. And so besides this so-called Z2 Ising DTC that we've looked at so far, where we were in a spin 1/2 submanifold and we had only Ising interactions present and we were only driving the 0 to -1 transition with this global rotation, we engineered 2 other DTC Hamiltonians, and one is also in a spin 1/2 submanifold where we have now Ising and spin exchange present, and another Hamiltonian where we're driving actually the whole spin 1 system. We first perform a rotation around the 0 to -1 transition and then 0 to +1 transition. And what this actually leads to is a DTC with a subharmonic at 1/3 of the drive frequency in the spin 1 case. I can show you experimental data for that. It's very much an analogy to the Ising case. At very short interaction times, there's no stable subharmonic response. You see that as we increase perturbation, these peaks move out. And now as you increase the interaction time, you get a locking at the subharmonic. And the subharmonic is 1/3. Yeah.
Looking at this perturbation, it looks maybe more robust than in the case of just the two-level system.
Yeah, very good.
Thank you.
Yes. Well, I'll come to that in a second. Yes. Okay. Yes, it even works in the presence of spin exchange interactions. Now, these are the phase diagrams, and as you figured out, yes, this was, I think, a cut probably somewhere here at 300. This is logarithmic scale, double logarithmic. You see that the phase boundary is wider in the case of this Z3 spin exchange and Ising interactions than in the case of only Ising interactions. Correct? Yeah. But if you look at it, generally look at the phase diagrams, then they qualitatively look very similar, but they have this feature. And what is that due to? Well, the point is actually that these spin exchange interactions, if you remember the Hamiltonian I showed you initially, spin exchange and Ising interactions have opposite sign. So what will happen is that the spin exchange will actually produce a screening field in the opposite direction of the perturbation and effectively reduce the perturbation strength. And that's why we get a wider phase boundary in the presence of spin exchange interactions. Okay, so that's at short time. Now if we want to look at the long time dynamics, we again looked at the lifetime. We checked the lifetime and of these signals. And what I initially had shown you is that we get this bi-exponential decay. And we get this, epsilon independent late-time decay. You see, these curves are all parallel to one another until you're sort of outside of the phase. But when we go to very long interaction times, we see a peculiar change. We see that if you look at the polarization decay, it very much resembles a simple exponential. You see simple exponential decay of your signal that is now epsilon dependent. That's not perturbation dependent. Yes?
Can you think of adding terms into your Hamiltonian to protect your time crystal?
For longer interaction times?
Yeah. Or like in general to have it to be more robust to perturbations. Like maybe you can think of adding terms so that like signs compensate and eventually you have a hyper robust time crystal. Maybe this is the same.
Yeah, I mean you would have to compensate for these effects that come into play here. So what we see here in this particular case is that there's dephasing occurring already within a single Floki cycle. Now you have to compensate for that. You can, if you know the origin of the dephasing, then you can. In our case, it's not so easy because, as I will show you, this origin is actually the interactions of the system itself. So it's not so straightforward, but yes, in general, yes. I think you can, but then also again only for certain types of perturbations. You can.
Yeah, I guess you have to really understand the origins.
Yeah. Okay, so we can try to find this crossover point from this, initial epsilon independent decay rate to this epsilon dependent decay rate. And so for that, we simply fit this the decay of the signal with the stretched exponential with the variable exponent beta. And what we see is that as the interaction time is increased, this beta approaches 1. And so we have this in this regime where beta is still small. This was the regime where we were kind of epsilon independent decay rate. And then in this upper regime where it saturates out, we see a quadratic increase in the decay rate. And this quadratic increase hints towards an instability of the DTC order. We initially required DTC phase to be robust against perturbation and also the lifetime to be robust against perturbations. And so if you see that now as the perturbation is changed, the decay rate drastically increases, this regime can no longer be called a time crystal. And so what's the origin of this instability? This origin, the decay rate increasing quadratically hints towards a Markovian regime, because that's exactly what you would expect if you had dephasing dynamics. Because then you can imagine you have your spin that you rotate imperfectly, and what it will do is it will dephase within one Floki cycle, and so then you effectively project it back onto the quantization axis, and then you do an imperfect rotation again, it gets projected back, and so each projection, it loses polarization by an amount of cosine epsilon, and so then if you do an expansion, you see that this corresponds to an epsilon square over 2 scaling of the decay rate. So we can characterize this crossover now for the 3 different DTCs that we've realized. For the case of, a set 3, so this 3T periodic time crystal with spin exchange and Ising interactions, we see that this crossover occurs earliest, and it takes the longest for this Z2 Ising case, where a spin exchange are absent. But in all of the 3 cases, once it saturates out up here, we can, up to some offset value in the decay rate, they'll nicely all overlap on this quadratically increasing decay rate. So we see some universal behavior emerging at this very long interaction times. And so, as I told you, this is due to some Markovian dephasing dynamics of the spins. And now the question is, what is the source of this dephasing? It could be dipole interactions or the environment. And to test this, we increase the interactions by a factor of 2 by simply using 2 groups of NV centers in the experiment, and so then you increase the density by a factor of 2. And what we find is that this crossover to this third regime, to this Markovian regime, occurs earlier. In this case, that's the first thing. And the second is that we can estimate the dephasing time due to the environment. We find that this is much longer than this, again, this crossover point. And so this really points towards the many-body system itself serving as the heat bath. And we've also, yes?
So why do we refer to that as a Markovian regime? Because, once it's very hard to see that this is Markovian so that the environment doesn't know about, or nothing comes, because Markovianity in some sense how you can think about it is that they have a system coupled to a path and nothing can come back from the path to the system. But when the many-body environment itself is its path, then it's very likely that something comes back, right? So
that there are some correlations left.
There are some correlations, right? So in that sense, Markovian just means that you have some dephasing and...
Well, you have some dephasing, but it also needs to, eventually nothing comes back. I think that's what you will also need in this case. I mean, we've performed numerical simulations by looking at an infinite range interacting system with random couplings. And what we find is that when we, for both cases, only icing or icing plus spin exchange interactions, that it eventually shows this for long enough interaction times, it shows this quadratic scaling of the decay rate. It occurs later for the peculiar case of only icing interactions, but in both cases it does approach that regime. Yeah. But it's a good question, yes. And so we think that the icing case is special, right, because it shows this sort of the latest the longest T star, so it enters this Markovian regime at the latest, and also it shows this the largest critical regime with a very distinct scaling. It's 1/√T scaling, while the other two cases, I mean, this is some scaling, but we actually don't know exactly what to expect because it's hard to find them. It's actually hard to model the system in the presence of spin exchange interactions. And so, yeah, now looking at these 3 Hamiltonians, we really see that depending on the peculiar nature of your interactions, you can get different thermalization dynamics. But we don't completely understand this behavior yet, so this is something that needs to be done in the future, yes.
So for the icing, you had the spin locking signal
Yes.
on, so that's counteracting dephasing.
That is also counteracting dephasing, yes.
Doesn't that increase? So
No, that's counteracting depolarization, not necessarily dephasing. Right,
it fans out and still sort of.
I think it's more.
Okay, but for Z2, Z3, there was no spin locking.
There's no spin locking, yes, it's in the very frame.
Because if you spin lock, then it's not T2 anymore. It's like T1 row or something. The coherence time. It's no longer just pure dephasing.
I think the extent that we see this shift up is not just explained by this effect. Yeah.
Not just this yeah.
Okay, this brings me to the end of my talk. I'd like to quickly acknowledge the team that's been working on this experiment. This is 2 graduate students, Harry and Junhee. In the lab, we have a very strong theorist, grad student, that now just left for a postdoc, Norman Yao, Sunwon Choi. And I'd also acknowledge theory collaborators Dimitri Abanin and Wenwei Ho, and our sample providers, and of course we're supervised by Michelle Lupin. To sum up, I've shown you a new non-equilibrium phase of matter, so-called discrete time crystal. That's a very sensitive probe of underlying thermalization dynamics. And we see these 3 different regimes emerging. A regime 1, where you can describe the system as being coherent closed system dynamics and a mean field approach. A regime 2, where the system starts very slowly absorbing energy from the drive, but because it does this exponentially slow, you can still see thermalism. You can still call this a DTC regime. And then a regime 3, where due to the interactions in the system, the spins dephase completely, and you can regard this as quantum xenodynamics. And this is now no longer a DTC. Outlook, what are we going to use this DTC for? Well, one nice application would be quantum metrology, that we could use this for enhanced sensing, because usually it's interactions and decoherence that limits the sensing to the standard quantum limit. And so in a paper by Sung-Won Choi, very recently he showed that if you use now this idea of a time crystal or of pulsed or flocate driving of a system to make it robust against perturbations, you can in principle also protect strongly entangled states, like for instance GHZ states, and then you can use those for enhanced sensing. And this will bring you down from the standard quantum limit to the Heisenberg limit. And also it can extend the bandwidth of the sensing. This is one idea, but very, very generally, we would like to go also with the system, this black diamond system, to lower dimensions, where, as I've mentioned at the beginning, and we discussed that in 2D, it's unclear if the system would be localized or still in this critical regime. And what we're currently doing is we're doing Hamiltonian engineering by using the toolbox that the NMR community has developed, using dynamical decoupling sequences to engineer certain types of Hamiltonians, or even just turning off the interactions completely. And then having a many-body system of n-spins and use that for enhanced sensing. Okay, so with this, I'd like to thank you for your attention.